I think Marianne already introduced me, but it was encrypted, so I'll introduce myself again. I'm Philip Paeps. I'm a FreeBSD developer, and when I'm not developing FreeBSD, I'm a troublemaker. I'm a consultant. I work for a number of different companies doing mainly embedded stuff, and I do this embedded stuff with all sorts of platforms, mainly small real-time operating systems, this open source operating system you may have heard of called Linux. And most recently, I'm also involved on an embedded FreeBSD project, which is new for me, since FreeBSD has always been the thing I run on my servers, and now it's also going to be the thing I run on my embedded platform. So I started playing a bit with FreeBSD, getting myself acquainted with how to use it as an embedded development platform. So I think the talk on the schedule was called for large and small beds. So I'm going to talk in the second half of my presentation a bit about how I got FreeBSD working on a large embedded platform and then on a smaller embedded platform. Ooh, it works. So a small outline to introduce you to the embedded world. I'm going to talk a bit about how it's different from other computing environments which you may be familiar with. Then I'm going to talk about my little console server, what it is, why I built it, and then the two platforms I built it on. And then I'm going to go into depth about how I actually went about doing this. And then I have a wish list, and there are about 50 people in this room. Maybe if 3 of you pick up items on my wish lists, that would be nice. So the embedded world is very nice. It's lots of very friendly people. But it's a bit different from the enterprise computing world. If you're working for a large company, working on a database platform, you can spend years doing a project. Or if you're in the automotive sector, I don't know how long it takes for a car to be built, but you have a moderate amount of time to build something. In the embedded world, not really. There's never any time. You will have your marketing manager breathing down your neck telling you that we have this great product, and we want it on the market yesterday. And then you tell them that your time machine is broken, that you don't have time to fix it. And then you negotiate with them for a while, and then eventually you will have about half the time you need to build a product to actually build it. Also, unlike the enterprise computing world, space is not free. My laptop has a gigantic amount of space. It's got hundreds of gigabytes of disk space. I have embedded platforms with 64 kilobytes of disk space. What disk space? ROM space. And if I want more, I need to, well, I can't get it. Because if you're building 100,000 of anything, that 1 or 2 cents it costs more actually adds up to a lot of money. So you're not going to get it. Your software will fit in 32 kilobytes, whether you like it or not. And the cynic in me says whether it works or not. And then there's a third item which is different between the embedded world and the other world or the real world is that people forget that electricity costs money too. If you run a data center and you have a couple of rows of racks with pizza servers and they each take 450 watts, what's another 450 watts? If you're already drawing 100 amps, 102 amps won't matter too much. It turns out that if you're a small battery-powered device, people get very upset if these things start drawing 2 amps. If this phone drew 2 amps, it would run out of battery in a couple of milliseconds. People would be upset. Also, if you run a consumer electronics device which is going to sit in someone's basement like an ADSL modem, over a year, if it takes a couple of milliamps or a couple of amps, it's actually going to really matter on the power bill. So those are a bit differences with the other worlds. Another difference between the enterprise world or the other worlds and the embedded world is that in the embedded worlds, there are intellectual property dragons. Legal uncertainty is not an option. If you are making money on a product, say you are selling remote controls or phones or other things and you're making money on them, then people will want to take this money away from you. These people are called lawyers, and they do anything they can to take money away from you. So any legal uncertainty you have is just not an option. There's this guy called Richard Stallman. He's quite popular in some circles. He preaches that everything should be free. And he has this license called the GNU General Public License, quite popular in some circles. And it's a very interesting philosophy, but one of the things it requires is that everything you make, you need to also make. Every piece of software you use will be free, but it will be free only if you also give it away for free. And give the source code and let people play with your source code, which is fine for many things. Your web server is lots of fun, but you don't want people to hack a payment terminal. Well, not if you're making the payment terminal and expect the money to stay inside. You don't want people to hack your payment terminal. You don't want people to hack your ATM. You don't want people to hack your X-ray detector. You don't want people to hack your satellites. Well, it's yeah. So GNU is not always free. Linux is a very nice operating system, but not always the best choice. So in addition to Linux as an embedded platform, there are also more traditional embedded systems. They are often proprietary and often expensive. There's a little company called Windriver. They make an operating system called VxWorks. And if you ask them nicely, they will give you a source code license, provided you also give them $60,000 or something. Should be fine. If you make a device which you sell for $30, they will want 3 cents. If you make a device that costs $300, they will want $3. So it's quite expensive. But it's also quite small. So traditional real-time or embedded operating systems are tiny. You can fit Microtron or another traditional embedded operating system in a couple of tens of kilobytes. You can fit VxWorks into hundreds of kilobytes, so this is definitely smaller than Linux. I have tried getting Linux down into order of magnitude hundreds of kilobytes, and it is quite difficult. The Linux kernel is all right, but you also want it to do something, and then it becomes difficult. Most of these traditional embedded systems are hard real-time, which is also most of the work I do is hard real-time. To explain what real-time is, if you have a machine putting cars together and you're putting on the windscreen wiper, real-time means that the robot gets turned on when the windscreen wiper is just tight enough, because if it's not tight enough, it'll fall off when you use it, and if it's too tight, the window will break and people around the car will be unhappy and bleeding. Most of these real-time operating systems are therefore very simple. They tend to be task switching or somewhat multi-threaded in one or another way, but they'll generally be running on one CPU. And they'll mostly be single application optimized. So FreeBSD and Linux, you can run hundreds of applications on them, provided you have memory and CPU time. A real-time embedded operating system, if you run one application, you're generally going to have to be happy with it. So, I think everyone should know FreeBSD. FreeBSD is a Unix-like operating system, a little bit like Linux, but only more so. It's derived from the Berkeley family of Unix operating systems starting in the 1970s. Some BSD developers give very nice talks about the history and how it came about. And one of the nice things about FreeBSD is it has a friendly BSD-style license, which basically says you can do anything you want with this software, provided you don't say that you wrote it, and provided you don't sue us if it breaks. Basically, if it breaks, you get to keep the pieces. You can contrast this with the GNU license, which also says you can do anything you want, provided you don't sue us, and if it breaks, you get to keep the pieces. But there's also 30 more pages explaining exactly how free your software should be when you use it. So it's interesting. One of the nice things about FreeBSD is it has an integrated build system. You type make world, and an operating system falls out. It won't be a very useful operating system, depending on your platform. It'll be useful for a desktop, not exactly for an embedded device. You can customize this build system to your requirements easily. This is different from the Linux world, where you type make and you have a kernel, and then, oh, you want to type something to the kernel, so you need to go and build BusyBox. You type make again, and then 14 applications later, you have an embedded operating system, and your chances of reproducing this operating system are exactly 0. And you have to write a lot of little scripts around it to make it work. With FreeBSD, you don't have to do this. I have another talk actually introducing the FreeBSD operating system, which I think I gave here 2 years ago, so I should probably give it again. Contrary to popular FUD, FreeBSD does support many of the embedded platforms. FreeBSD runs just fine on ARM. FreeBSD runs just fine on PowerPC. FreeBSD runs better and better on MIPS, because I'm working on it. Unfortunately, FreeBSD is not all good. If you've worked with Linux, some of these points should be familiar. FreeBSD, when you make world, is perhaps somewhat larger than desirable. If you just run make world, I think we're now up to check your time. We're now up to about 130 megabytes for a kernel and a whole operating system, which is, the nice thing is you have Kerberos with it. You have a DNS server, you have a DHCP server, you have everything you need on your desktop or on your server. But on an embedded platform, you would like that to be smaller. It's relatively simple to get FreeBSD down to tens of megabytes or even 10 megabytes, but anything beyond 10 megabytes is difficult. Whereas I've got Linux down to a workable Linux system you can easily put into 4 megabytes without too much effort. You build the Linux kernel for ARM, you build BusyBox, and I think if it's 4 megabytes, you've probably not tried very hard. The FreeBSD operating system inside the kernel is also still missing some bits which have been in Linux for a long time. Linux has something called the MTD subsystem, Memory Technology Devices Subsystem, which makes it trivial to write flash drivers. On Linux, I just did that for a customer, I think 2 weeks ago. I wrote an MTD, a flash driver for a certain NAND chip, and it took me 3 hours and 400 lines of code. On FreeBSD, writing an AMP driver takes you 3 weeks and 3,000 lines of code, and then maybe it will work. Well, that's maybe exaggerating, but it will take you a little while to write your device driver. It would be really nice, and it's on my wish list if someone wants it. If someone could write a NAND or a NOR device abstraction layer, like in Linux, but it doesn't have to be exactly the same. Another downside of FreeBSD, from the perspective of someone technical trying to sell it to his management, is that it's fairly difficult to compete with Linux. Linux is everywhere, and even your marketing manager knows Linux, probably because it's running on his phone. So Linux has a lot of mind share, and it's difficult to compete with that. Also, Linux is not as bad as it used to be. There's still, well, I see Linux people laughing, but there are certain parts of the Linux kernel, if you look at them hard enough, you just want to take a shower. How did they come up with this? The Linux kernel is actually becoming much cleaner since Linux 2.6.18 or 20. They've been doing lots of work on cleaning up some of the scarier parts of the Linux kernel, so it's not too bad. But it's becoming more and more difficult just to compete on features. Well, it's always been difficult to compete with Linux just on features. FreeBSD does have a number of really nice features, but they're not really relevant in the embedded world. FreeBSD has ZFS. You're not going to run ZFS on an embedded platform. It wants 1.5 gigabytes of address space. If you've got a tiny 32-bit CPU, no, you can't have 1.5 gigabytes of address space. I need this address space. FreeBSD comes with dtrace, which is great, but it's only great if you have a gigabyte of memory. It's recently talking to a Linux gentleman who's laughing at me. You want an extra gigabyte of memory? No, you can't have another gigabyte of memory. That's silly. That's silly talk. Gigabytes of memory cost money. So all the FreeBSD bits are mainly geared to enterprises, but embedded platforms take many shapes, as I said, larger beds and smaller beds. So that was the ranty part of the talk. Now let's go down to the technical part of the talk, which is much more interesting. I built a console server because I'm silly, and I did it twice because I'm very silly. To remind you, a console server is a required part of any hacker lab. It's a little device that allows you to sit in your sofa to work rather than sitting in the lab with all this noisy machinery and all these people around you. You have this tiny machine sitting next to your hardware, which is either loud or noisy or smelly or electrically unsafe or all of the above. And it allows you to go and sit in the sofa and do your work next to the coffee machine. It generally has serial cables, so you can talk to the console of your machine without having to pretend to be a keyboard. And usually it has more than one serial port, so you can have one on the console and one on the UART, on the debugger, so you can debug your kernel when you inevitably break it. It usually also has a couple of general I/O pins, so if you really break it, you can turn the power back on. It should, I feel, also have smoke detectors, so if you really break the hardware, it stays off. But anyway, unfortunately, console servers are also very popular in large data centers because if you have a rack full of servers sitting in a data center somewhere out in, I don't know, the middle of nowhere, far away from where people live, you don't want to send your employee out at great expense when your server fails. You want him to just sit in his sofa or at his desk or wherever, log in remotely and fix whatever is broken, ideally without the time of a drive or without any time. So unfortunately, this makes these console servers very expensive because data centers have lots of money. If you have a whole floor full of servers, adding a unit of a couple of €100 extra to your rack isn't going to make a difference. So you can buy retired ones on eBay, but if you are married, you're not going to be allowed. You're not going to be allowed to. If you live in a small apartment, you probably don't want to because they are loud and clunky and they're power hungry. So yeah, so you want to build it yourself, and also because it's also fun to build these things yourself. So let's talk about the two things I did. The first console server I built was on a fairly big platform. It's Sucres. It's a Danish gentleman who went and designed single board computers, mainly for use in telecom environments. They're very good. They're very popular for people building wireless access points. They usually have a couple of Ethernet ports, and they're very nice for this. So they've got a 100 megahertz Intel compatible CPU. It's actually mostly a Pentium. Mostly, it doesn't have MMX or any of those fancy instructions, but it's mostly a Pentium, so you can do your development on your host environment, and as long as you use conservative CPU flags, your binaries will just run without any fiddling on the targets. It's got lots and lots of memory. It's got 32 megabytes of RAM, which is, well, by my standard, that's lots and lots of memory. It's got compact flash storage, which is quite handy because it's the same card that fits in your camera. You've got a reader sitting in, well, probably hiding somewhere under a large lump of cables in your laptop bag. This makes it very easy to get code on the boards, which I'll talk about later. Unfortunately, when it comes to a console server, this device is not very useful. It's only got 8 GPIOs, so that's 8 power switches, or 4 more UARTs, and it's only got 1 real UART. So if you want to do anything timing, well, if you want to do anything timing sensitive, you want a real hardware UART. If you just want to control an embedded board, you can bit bang the GPIOs to be another UART. This is not fun. So the maximum of UARTs on this board is probably 5. And then you can't power off and on your machine remotely. So not so very useful. It doesn't have USB on boards. This board is, I think, from the early 2000s, and USB was already quite popular then. Now USB is pretty much ubiquitous. It used to be universal, now it's ubiquitous. But it does have MIDI PCI and some other big buses, which I'm not familiar with. Power consumption is enormous. It's 14 watts, which if you run it for a year probably comes to, I don't know, moderate expense. So after working with that board, I went for a more traditional embedded board. I found an Atmel AT91 board. It's an ARM v7. For those familiar with ARM, it's got 64 megabytes of RAM, so even more memory than this other board, but I think 8 megabytes of those are SRAM and only 48 megabytes is SDRAM. I don't remember exactly how it's divided. It's got 16 megabytes of onboard NOR flash, which I'll talk about in a bit. It's got 32 general purpose IOs, which is a much more reasonable number. It's also the width of a register, so a single bit, a single pin. This makes life easy. It's got 4 hardware UARTs. It's got USB, and then it's also got the usual complement of embedded buses. For those familiar with them, there's a whole list of them. But the main one I want to mention is it's got SD, so you can have the smaller SD cards. You can stick your code on there as well if you don't want to deal with the NOR. And the power consumption is half an order of magnitude less than the Intel boards. So, yeah, feature comparison. I'm not going to read all the bits out, but it's basically your usual trade-off, cost versus ease of development. The Sucres is moderately expensive, also not just to buy, but also to run. But it's really easy to develop for. The Artila ARM board is cheap, especially, well, I think a development board The Socrates board, I think, was €200 or something, or €300, I don't remember. The Artila board, the development board, was €100. But if you want to build 100 devices around this ARM chip, it's going to cost you a lot less than it would cost you. Every single Socrates will cost you the same price. The ARM, you get the degenerative pricing. So yeah, lots of fun. So I promised to tell you something about the NOR flash and about getting code on this board. The development phase is the same for both boards. You can netboot them. With FreeBSD, this is trivial. With Linux, you have to always fiddle around a bit getting, which TFTP daemon works this week. There's about 3 TFTP daemons, and they sometimes work. On FreeBSD, there's one, and it always works. And FreeBSD comes with a DHCP server and all the other bits you need to netboot the boards just there. I'll talk a bit more about my development setup later. You can just, on both devices, you can have your rootfs sitting on NFS, just boot your kernel over the network, jump into it, and you're set. And FreeBSD makes this all very, very easy. The production system, the Socrates just runs from CF cards. You plug it into your reader, you stick your code on, you stick it into the board, see if it works. If it doesn't, you unplug it and do the same dance again. The Artila has NOR flash on board, which is a bit more tricky. The problem is that, well, for me, this is not too tricky. I've got a Lauterbach debugger sitting on my desk, so I just plug JTAG in and I flash it. But for most normal development environments, this is tricky because you need to go, you can't write NOR flash directly. You need to speak a little protocol called CFI to it. And the onboard bootloader of the Artila system doesn't speak this protocol. It can read the NOR flash, but it can't write it. It does speak XModem and TFTP, but I think it would be a lot handier if it would also know how to flash its damn memory. So you load a binary over TFTP or over XModem into RAM, and then you jump to it. And then if you want to keep it, somehow you will need to flash it. On FreeBSD, I have written a little utility that will make it do it for me. It's just a kernel module that reads an address in memory and a size, and then it goes and bit bangs the CFI down to the NOR. It's just tricky, but not impossible. Yeah, so FreeBSD is a development workstation. I've been using Apple and Linux as my development workstations. So now I'm using FreeBSD as a development workstation for this, which is actually remarkably sane. Everything you can do on Linux, you can also do on FreeBSD. It runs X11, it runs every window manager you can possibly imagine. And the nice thing about FreeBSD is that the base system contains all the things you need, which is a breath of fresh air from Linux. If you install Linux, you will have a desktop operating system, but you type CC and it tells you it's not there. I don't know. How do you live on a Unix machine without a C compiler? I don't know. FreeBSD base system has everything you need and more to build embedded systems and then to go and debug them, which is nice. Other bits, if they're not on the base system, you can easily get them from the ports tree or the package tree, which is the same as on Linux. Nice about FreeBSD is that it's trivial to netboot. Linux is also trivial to netboot, but FreeBSD makes it really, really easy. It's you just point TFTP boot, the default configuration, you uncomment one line in inetdealconf, and you have a netboot server, and it just works. Also, once FreeBSD works, it tends to keep working, unlike Apple or Linux machines, which start crying after a while if they've not seen the internet. Help, help, your bits are old, you need new bits. This doesn't happen on FreeBSD. I have a whole slide dedicated to documentation. If you've ever tried to do any work on the Linux kernel, there's a nice directory in the Linux kernel called documentation. It's at the top level, spelled with a capital D even. There's nothing in it. There's a lot of files in it, but they're either out of date or they only have a tenuous relation with reality. And they document the pieces of the kernel you don't need. I don't need to know how the ATA subsystem numbers its minor devices. I want to know how to write a flash driver. And last time I looked, there was no documentation about this in the Linux kernel. The FreeBSD kernel is extensively documented. We have man pages for everything. Every public kernel interface should have a manual page. Some of them don't, but they will in due time, we promise. As I said, even the kernel is documented. I promise to say more about this integrated build environment we have on FreeBSD. We have a make file under user source, which if you type make, will sit for a couple of hours and build you everything. It'll build you the whole operating system for every single platform you could think of, and it will do this well, but it's not ideal. You can tell it not to make things, but you can tell it what you want made. If you want a tool chain, you can say make tool chain, and it will make you a tool chain. Very nice as well as you can do make target env, and it will set your path accordingly for the target you're working on, and you will have your cross compiler and all the bits you need sitting in your path. You can do partial builds with it, so you've started building your kernel and you discover halfway through that, oh no, I've forgotten this or this bit, or I made a typo on this or this line. You can Control-C, and you can go back and fix whatever problem you need to fix. And there's no need to invent another wheel on Linux. If you want to, every company I've worked on which uses Linux as an embedded platform has another set of scripts to work to build the world. There's a system called BuildRoots, which is quite popular in the Linux world, but it builds a whole tool chain, it builds a kernel, it builds BusyBox, it builds all sorts of things, but it builds them all over again every single time. It has no support for partial builds. So every time you want to make a build and you change one line in some kernel device driver, it wants to build your tool chain again. I don't want to rebuild my C compiler when I've changed one line in a device driver. On FreeBSD's integrated build environment, this is not the case. You just fix it, and usually the dependencies in the make files work too. They'll spend maybe a minute or so cooking the dependencies out, but at the end of the day, the only file that's recompiled is the one you've changed, and then the only files that are linked are the ones that file is linked to. So it's pretty nice. Also in the FreeBSD build tree is something called Nano Bsd, which was written by Paul Henning Kamp. I think he wrote it in anger, but he wrote it originally as a makefile, and more recently has become a shell script. It's basically a wrapper around make world and a couple of shell scripts that drill the image down to what you need. So you have a little config file, you say, I want this, 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 I want that, I want that, and I don't want this, 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 and this. And then you type Nano Bsd, and out comes a disk image, which you can just, if you're running on the Socrates, you can just DD to your CF cards, plug it in, and it'll go with 90% probability. And if it doesn't go, it's easy to debug. It's, yeah, as I said, it's optimized for producing disk images for CF, and the layout is also very much CF optimized. What it'll do is it'll create 3 partitions in a DOS MBR, one for your running system, one for your fallback system if the running system breaks, and then it'll have one partition in the middle for the configuration files. So it makes upgrading easy. You just flash the fallback partition, and then you boot from that one, and then the one you're not booted from becomes your fallback partition. So it's really nice. It also chops the FreeBSD world down to tens of megabytes. I think a default Nano Bsd build comes out to 64 megabytes, which is a convenient size for CF cards. But it's still quite large, say, for the Artela board, which has 32 megabytes of NOR or whatever it was. So we want half of that size. So there's a wonderful tool called CrunchGen, which is very, very old. I think it predates BusyBox. BusyBox is a Linux tool, which is a single binary with mini versions of all the tools you want. CrunchGen is a bit different. It takes the full application, and then it does all sorts of evil with it to try to make it smaller. So it looks at, well, usually the linker is pretty good at stripping out symbols you don't need from a statically linked binary, but the linker is not good enough, so you still have bits in these binaries you don't need. CrunchGen goes and finds them and chops them out. So you'll end up with a FreeBSD system that's easily under 10 megabytes. CrunchGen running on a Nano Bsd image, which is, I think, I had a Nano Bsd image which was 18 megabytes, and CrunchGen chopped that down to 8, which is pretty good. I have no idea what it chopped out, but everything seemed to work. It's actually still used in FreeBSD in production as well. It's used to crunch the binaries in /rescue, which if you've ever had a server crash and burn on you, you really appreciate. And then I was going to talk a bit, that was the bit about my console server, and then I'm going to talk about my wish list. I would like the FreeBSD bootloader to be friendlier for development. On Linux there's a bootloader called Grub, which is popular on PCs, and there's a bootloader called U-Boot, which is popular in embedded environments. And both of these bootloaders have a command line, and they have tab completion in the command line. And U-boot can flash NOR, U-boot can flash even some NAND flashes, and all sorts of other things. The FreeBSD bootloader can't do this. I would really like the FreeBSD bootloader to be able to do this, because it would make my life a lot easier. As I said, especially for the NOR flash, it would be nice if I could tell my bootloader to go into the FTP an image, stick it somewhere in memory, and then please go and flash it. So I don't have to, every time the power goes out, find a serial cable to plug into my serial box to tell it to load a new image, and then find the new image on my laptop, of course, which I don't back up output files. As I mentioned earlier, I would like a generic flash layer in the kernel. I've been told that a gentleman from New Zealand is working on this, but would appreciate some help. So if anyone here feels themselves capable or is otherwise bored enough to do a flash layer, I would be really happy if people did. If you've used FreeBSD at all, you know about package adds. It adds binary packages to your system. Unfortunately, it adds binary packages to your system. It feels that it should only be called for the host it's actually running on, which is suboptimal, because if you run on Intel development workstation and your target platform is ARM, you are going to have an Intel package, and it will not run on your ARM, or not very well. Well, not at all, actually. So I would like package add to take a parameter, -t ARM, and just download the package, put it somewhere safely, and I will install it on my target platform later, or maybe it should take a directory. It should be a matter of an hour or two to write, but no one has done it, and I'm not touching it. I would like the better integration of CrunchGen with the builds. Currently, CrunchGen is a little underappreciated but fairly well-documented tool. It's installed by default, but the build system has no hooks for it. It would be nice if there was a make crunch target or something in the make file. It should also be very easy, but no one has done it. And then I think this wish list used to be quite long, but it's got a bit shorter. So I'll tell you a bit about what I'm up to currently. Currently I'm working for the University of Cambridge on a platform called Cherry, which is a MIPS-ish. And it's a 64-bit only MIPS, and it's going to run FreeBSD only. So it's keeping me out of trouble and off the streets. The University of Cambridge is happy to pay me to fix some of the items on my wish list, which is why it's getting shorter. I will probably pick up the bootloader item if I find enough hours of contiguous free time. So I expect this to be my talk next year, or maybe the year after here. And I think that puts me with 10 minutes of time for questions, or comments, or insults, or...
Някой да има въпроси?
Did I talk too fast and is everyone asleep?
Or you might be crystal clear.
Yes, it might. Clear as mud. There's a question.
It's real-time operator can't work on real-time this BSD.
FreeBSD. FreeBSD is not a real-time operating system. The nice thing about real-time is how real do you need your time to be. If you want milliseconds or tens of millisecond precision, FreeBSD will probably work well for you. If you want nanosecond precision, FreeBSD will probably work badly for you. Or you will have your lawyers complaining about FreeBSD when it breaks something. You should be able to do it. There's high precision timers in FreeBSD very high precision timers since FreeBSD 5, but it's still, the kernel is running on multiple CPUs, so if you're on a single CPU, you can probably have moderate real time up to hundreds of nanoseconds. So sub-millisecond precision, I'd still be careful. But it depends, of course. If you have only one process running and you know that you've analyzed your system and you know that it can never swap, you know that no task can be preempted, then you can probably assume that it'll be safe. But it's pretty cheaper to just buy VxWorks if you need that kind of real time. If that answers the question. Another question here.
Two hardware questions.
Okay.
What is the FPGA on this Cherry board?
It's a gigantic Stratix 4 from
Ah.
Altera. It's we're using the 250,000 LE version.
Yeah.
I don't know what it costs. A lot of money.
And what is the speed of Ethernet interfaces on this board? There
It
is
has
four-
it has 4 gigabit max.
Gigabit. Okay.
It has 4 gigabit max,
Perfect.
but it has I have a laser pointer somewhere. Marianne promises me
Yeah.
on the alleged keyboard.
Yeah.
There's a button. This is actually PCI Express coming out. So
And-
it's 8-lane PCI Express, so you can put a 10 gig Mac inside your. You could put a 10 gig Mac into the FPGA, and then stick the PHYs and all the other bits you need on the.
And can we buy this board online?
I think this development board costs $13,000, but Altera will be happy to sell it to you.
$13,000.
It's
Okay, thank you.
but yes, the aim is actually to make. We're working with this board, but we want to make the CPU. It doesn't need the whole CPU. It doesn't need the whole FPGA. It takes currently this Cherry takes, I think, 10% of the area on the FPGA. So you can probably put it in a small Xilinx in a Spartan or something. But we're currently 1 year into a 4-year research project, so maybe my talk next year will be more interesting. More questions?
Okay. Do you know if the items on your wish list, is the situation with them somewhat better in other BSDs?
Flash layer, I think NetBSD is probably in a better shape. I know that NetBSD is in a much better shape when it comes to cross-building packages. NetBSD, I think, it's been a while since I've used package source, but I think it should be possible to build a package on NetBSD for another architecture than the one you're on. CrunchGen on NetBSD, I have absolutely no idea. NetBSD's bootloader is still the old, what is the old BTX switching thing? You know, two kernels for the price of one. But I think in terms of packages, NetBSD is in a lot better shape. OpenBSD, I have no idea. I know it exists. Dragonfly BSD, likewise. Apple has a very nice bootloader, but it works very well on ARM, and I'm sure they have very nice development tools, but yeah, they're not open source. Anyone else?
Други въпроси? Oh,
Just in time for coffee.
thanks, Phil.
Thank you.